So welcome to Math331 problem solving lecture 5. What we're going to do today is we're going to continue the arithmetic mean, geometric mean. We have a visitor, so we will be on extra good behavior today. You are welcome to participate as well. Have you seen the arithmetic mean, geometric mean before?
Yes.
Okay, excellent. So the arithmetic mean of numbers is a1 plus an over n. The geometric mean is a1 times an to the 1 over nth power. And we will typically assume the AIs are all greater than 0. If any of the, I'm not quite sure why this is bouncing around so much, but if any of the AIs are negative, the problem is not necessarily interesting. If any of the AIs are 0, it's also not interesting. And we talked about how to get some intuition by doing special cases. And when you do some special cases, you take the limit as one of the A's goes to 0, you see the arithmetic mean should be at least as large as the geometric mean. So the only possible inequality we could have is, AM of A1 through AN is greater than or equal to the geometric mean of A1 through AN. And we discussed we could assume the A's sum to some constant, or maybe even better, the sum of the A's divided by n equals some constant, or we could assume the product is a constant. And this is because the two sides both have the same units. So if you make A be meters, this is going to be in units of meters. This will be meters to the n to the 1 over n will also be meters to the n. We proved n equals 2. So we proved n equals 2 two different ways. So my cell phone was actually on for a few seconds because we had a visitor, and I wanted to just leave it on in the off chance. So you had your opportunity. It's free breakfast. Whoever's phone rings has to provide breakfast, and so if my phone had rung. How do we prove n equals 2? We did one by brute force, and we saw that basically this was coming from the gradient inequality, x squared is greater than or equal to 0. And then the other one was a geometric proof. If we're proving things by induction, do we need to prove the n equals 2 case? No, what case do we need if we're doing things by induction? N equals 1. Sometimes it's not a bad idea to do a second case as well to build up intuition, especially if the first case is very trivial. If n equals 1, we are comparing a1 over 1 to a1 to the 1 over 1 power. This is not an exceptionally challenging inequality to prove. And proving the case of 1 may not really give you much intuition as to what's going on. All right. So what I want to do now is I want to shift to different proofs. So I'm going to give two different types of proofs of this. The first, hello, no problem. The first is using stuff from multivariable calculus. So how many of you remember Lagrange multipliers? Okay, I see one head going down like this. Okay, so since none of you had me for multivariable calculus, correct? Good, so then I'm not responsible for this debacle, and so we can just work on fixing it and not try to assign blame. But if you want to assign blame, it's okay because it's not going to land on me. So Lagrange multipliers is extremely useful. How many of you are doing economics as well? All right, so you might see Lagrange multipliers in a lot of economics problems. And it basically deals with constrained maxima. So one of the reasons I want to do this is not just to prove the arithmetic mean, geometric mean, but to give you another approach to attack problems, another useful technique, review some things you should have seen in multivariable calculus, and it will also allow us to look at problems in interesting ways. So for Lagrange multipliers, you need a constraint. Well, we have two natural constraints. Either the product is fixed or the arithmetic mean is fixed, and then we're varying everything. It's not quite a pure Lagrange multiplier, because with a pure Lagrange multiplier, let's say we had this constraint equals c, we would allow the a's to become 0 or negative. We have the additional constraint that the a's must be positive. It turns out that's not going to matter, but you just have to be a little bit aware of something like that. All right, so let's deal with Lagrange multipliers. So we want to maximize or minimize f of x subject to g of x equals c. Okay? So we have constraints. So in calculus, if you have a function that you want to maximize and there's no constraints, what do? God, I hate doing this. All right. So tell me where my speed is largest. All right. Where was my speed largest? I really wish we had somebody in that room now who could tell us.
The moment before you hit the wall?
I wouldn't say the moment before. I would say as I'm hitting the wall. Was my derivative 0 there? No. It's not enough to look for where derivatives are 0. What else do you have to check? The boundary points, okay? I do not want to do this again. This is temporary housing. I do not know how well these walls have been placed. I was half expecting the board to fall down. But you have to check boundary points. Now, in Calc 1, checking boundary points is not a big deal. You have at most 2. But once you get to multivariable calculus, now you have a whole region to check. And that's essentially the constraint. And so Lagrange multipliers helps you figure out these constraints. If your boundary is nice, say you can parameterize your boundary, then you could just say, oh, I want, say, maybe a circle. Maybe I can parameterize that by theta, and then we get a new function, and I would just write my old function as a function of that new variable on the boundary. And you could try to do Calc 1 games. But as you start to get more and more complicated surfaces in 12-dimensional space, this is not a good way to go. And you want to have a more convenient way of attacking everything at once. So here's the idea. You solve for the gradient of f. Does everybody remember the gradient of f? It's the vector of partial derivatives. At some point x equals some multiple of the gradient of g, and g of x equals 0. So we have n plus 1 variables. So the variables are, say, x1, xn, and lambda, and we have n plus 1 equations. We have df dxi equals lambda dg dxi, and then we have g of x equals c. So the idea is we have enough equations for all the variables we have so that there should be a solution. And the hope is that there will only be finitely many solutions, and then you can just check the finitely many solutions. So this is the procedure. The question then becomes, why does the procedure work? So imagine here's our surface. G of x equals c. And I need a little bit of calculus knowledge. So here's the gradient of g. So I need that the gradient of g is normal to the surface. It's the direction that is perpendicular. Is everybody comfortable with that from Calc 3? Willing to accept that? If you think of a sphere as g of x equals x1 squared plus xn squared is r squared. The normal to the sphere at any point is the radius, is in the same direction as the radius. And here you'll get the gradient of g is just 2x1, xn is just twice the radius vector. This is not a proof. This is just one special case. But at least gives us some intuition. So the gradient of g is the direction of the normal to the surface. It's where the surface is changing the fastest. Anything tangent, I'm basically staying in the surface. So imagine now I want to find a place where my function is optimized. And imagine at some point this is the direction of the gradient of f. So the gradient of f is not in the same direction as the gradient of g. Well, what we can do now is we can write the gradient of f as something in the direction of gradient of g plus something perpendicular to that, something in the tangent plane or the tangent hyperplane. So I would write my gradient of f like this. So now, could my function be maximized if I stay on the surface? Could it be minimized? No, because if I move in this direction, if I move tangent to the surface, I'm going to stay in the surface, and my function is going to be increasing in this direction, and it will be decreasing in the other direction. So it can't be a max, it can't be a minimum. So what this tells you is that if you have a maximum or minimum on the surface, the only way it can happen is if there is no component of the gradient of f tangent to the surface. Or in other words, the gradient of f must be completely aligned with gradient of g. So you need grad f to be parallel to the gradient of g. If the gradient of f is parallel to the gradient of g, do we have a maximum or minimum? Yes or no? Okay, why?
Well, I think if it's parallel, the only way that it's going to be, I don't even know what the other line is going to be called, but
The tangent line?
Yeah.
There'll be no tangent line.
It's
Yeah.
parallel?
If it's parallel to gradient of g, then grad of f and grad g are in the same direction.
Right.
So do we have to have a maximum there? In one variable calculus, if the first derivative is 0, do you have to have a maximum? So let's go back to Calc 1.
Wait, a maximum?
Or minimum, maximum or minimum.
Okay.
Do you have to have an extreme point if the first derivative is 0? No. This is the difference between a necessary condition and a sufficient condition. It is necessary that the gradient of f is parallel to the gradient of g. It's not sufficient. So this is necessarily, but not sufficient. If the gradient of f is not parallel to the gradient of g, there is no way you can have a maximum. There's no way you can have a minimum.
When is it that you have it equal to the derivative is equal to 0 and there's not a minimum and maximum?
So let's take the function f of x is x cubed. If you plot this function, I was going to get to this function, so it is a good question. The plot of this function looks like this.
Yeah.
And so f prime of x is 3x squared. So you do have a critical point at 0, where the first derivative is 0, but you do not have a maximum, you do not have a minimum. It's annoyances like this.
I see.
So what you would have to do here is you can't use the standard, you can't use the second derivative test here, because the second derivative is 0. The first derivative test still works, though. If you look at the first derivative, f prime is positive, 0, positive. So you can see that it's not going to be a maximum or minimum. You would need to go negative, positive to have a minimum, or positive, negative for signs to be maximum. So this is not going to tell us that we have a maximum or minimum, but if we're going to have any hope of having a maximum or minimum, this is where we have to look. Okay? So I forgot to plug in my computer. We should have clearly enough battery power for this class, but not sure about the next one. But the idea is, or the hope is, that there are so few points to check that it's not a big deal. That when you try to solve the system of equations, there aren't that many options. It's much better than checking every possible point, all the infinitely many points that we started with. So now, let's try to apply that to the arithmetic mean geometric mean problem. So we have a couple of choices. We want a constraint. The constraint should be either the arithmetic mean is constant or the geometric mean is constant. It doesn't really make that much of a difference. I have no idea why the computer is going up and down, but okay. Any thoughts as to which would you rather do, arithmetic mean as the constraint or the geometric mean as the constraint? Or does it really not matter? It really doesn't matter, because whichever one is the constraint, the other one is the function, and we have to take the gradient of both of them. So it's essentially going to replace lambda with 1 over lambda. So it really doesn't make a difference. So let's call g of x to be x1 plus xn over n minus c as the constraint. And then we'll have f of x will be x1 xn to the 1 over n. All right, so now we need to calculate some derivatives. So the gradient of f, when I take the derivative of everything, I'm going to get a lot of things. So it's going to look like df dxi. Let's just look at one term. df dx1. Because if we can do the first one, we can do all the other ones. It's going to be 1 over n, x1 through xn to the 1 over n minus 1. And then we have the derivative of the whole thing in here, right? Which will just be x2 through xn. Okay? So we want to try to make things as nice as possible. I'm not moving. So when you look at this, what is this screaming out at you to incorporate?
Like from 1 over n minus 1 to get it to a 1 over n as many times as you want.
So we could do that. In fact, when we put in the x2 through xn, that's going to cancel the negative 1 for everything. And so when you simplify, you get 1 over n, and you'll be left with x1 to the 1 over n minus 1. And then you'll have x2 to xn to the 1 over n. Right? How should we group things now? Does this look almost like something we know? Yeah, it almost looks like f. So we should put this x1 to the 1 over n in here, yes? And so when we do that, we'll get 1 over n, f of x, and then we'll have x1 to the negative 1, so we'll have 1 over x1. And the nice thing about this is all of the terms will have this f of x over here. So it makes the algebra a little bit cleaner and nicer. I'm going to try moving the sound system a little bit lower and see if that stops the motion. All right. Here we go. Okay, so now we have our expression over here. We can do it for all the other ones. And I'll write very high. So we get that the gradient of f is going to be f of x over n, and then 1 over x1 dot 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 1 over xn. Okay. What about the gradient of g? What will that equal? So what would the gradient of g be? Yeah, just 1 over n for every single component. So solving grad f equals lambda grad g, the only way we can do that is all the x's have to be the same. That implies x1 equals xn. And then, since x1 plus xn over n equals c, this implies each xi is just c? Yep. Okay? So we get that the only candidate for an extremum is when they are all the same. All right, now what do we do from this point? So check it. So if we check it, we will see that it's an equality. And then how do we go from this to the function f it has its smallest value there? So this is where you need to use a little bit of analysis. Okay? So let's see what happens if we just move it in significantly closer. So we need to use a little bit of analysis at this point. Okay, we will get the arithmetic mean equals the geometric mean here. And then how would you go and make this the rest of the work? So I will leave that to you to ponder and just think about the rest. Right? But this was a nice way to review a really good technique. What I want to do now is I want to do backwards induction. So how many of you have ever seen backwards induction or hopping induction, bunny induction? So what we're going to do is we're going to prove it's true when n is a perfect power of 2. And then, once we have it for a perfect power of 2, we'll then go backwards and get all the values that we missed beforehand. Okay? So this is the second proof method. Hopping or backwards. So again, part of this is I really want to introduce you guys to good techniques. How many of you have taken linear algebra and seen the Strassen algorithm for multiplying matrices?
I saw it in computer science class.
Okay.
I saw it in linear algebra.
So there are certain crimes against humanity. One of them is teaching linear algebra without talking about computational aspects. So how would you find the eigenvalues of a matrix? Do you remember from linear algebra? How do you find eigenvalues? Yes, the determinant of A minus lambda I equals 0. Have fun. Right? This is a computational nightmare, especially if you have a 10,000 by 10,000 matrix. You would then have to, you do not want to try to solve polynomial equations like this. It's a myth. There are much better computational techniques to do this. And a huge part of the subject is how do you do these computations efficiently? If you try to do this, you have to worry about numerical stability if you try to solve something like this. Well, how do you multiply matrices? So if I want to calculate, say, A times B, if they're both n by n matrices, each entry is going to require n multiplications. There's n squared entries, so you would expect that this would be on the order of n cubed operations. So naive, it's going to be of size n cubed. And there's something called the Strassen algorithm. So it's not one of those days. And you get n to the log base 2 of 7. All right, if this is the log base 2 of 7, how should I write n cubed? Yes?
N to the log base 2 of 8.
Yes. So the Strassen algorithm is a very clever way of saving one multiplication. Now, there's no such thing as a free lunch. You have to do a few more additions. Additions are cheap relative to multiplications. So I will send you a short little link to read about the Strassen algorithm. It's worth knowing about this. That things that seem like you can only do it one way, no. There's often many ways you can do it, and computationally some of them are much, much better. It is hard to appreciate until you really work in the subject just how awesome this is. It's like, really? You're excited about replacing an 8 with a 7? Yes. Because if n is of size 10,000 or 100,000 or 1,000,000, then any power savings is enormous. Now the Strassen algorithm is initially done just for 2 by 2 matrices, and then you build up. It turns out it's really nice if your matrix dimension is a power of 2. This is going to be very similar to the hopping backwards induction. If things are powers of 2, there's often nice ways of collecting things. And so what you often have to do is if your matrix is not a perfect power of 2, pad it. Just put in, here's your matrix, and then just put in a bunch of 1s over here and 0s over here, and just pad it so now it's a perfect power of 2. And now you can use the Strassen algorithm. So what we're seeing here is not just a one-hit wonder. This is a real good technique. So we're going to prove it by backwards induction. So do for n a power of 2. All right. So the question is, have we already done it for n a power of 2? And the computer just nodded yes. Good job, computer. When did we do it for power of 2? Well, we said n equals 1 is trivial, and that would just correspond to 2 to the 0. And we also at least did it by brute force for two things. So no matter what, we are definitely covered here in having done the basis case. Okay? Base case is done. Now let's do the inductive step. So assume true for 2 to the m, show 2 to the m plus 1. Right. So I'm going to write my number as x1, x2, x2 to the m, y1, y2, y2 to the m. So this is going to be 2 to the m plus 1 numbers. We need to show that the arithmetic mean of this is greater than or equal to the geometric mean. But by induction, what do we know? So what must be true?
It's true of each of the halves.
It's true for each of the halves. We know x1 plus x to the 2m over 2 to the m is greater than or equal to x1, x 2 to the m to the 1 over 2 to the m. And we know y1 plus y2 to the m over 2 to the m is greater than or equal to y1, y2 to the m to the 1 over 2 to the m. Now what should we do? Yes?
I mean, if you just look at all the y's together as one number and all the x's together as one number, then you just have to multiply it by 2. So by the inductive step, then you're done.
So we basically now we want to apply the inductive step to which value? What value of n? 1. So the number 2 to the first. So we actually did need to do the base case with two elements. So this goes back to the Kathman theorem, that we need to know that it's still true for that one special case, and then we're going to propagate that one forward. So for here, it's not enough to just go through things. We needed that one special case. But once we have that case, we can use it. All right. So now we've got to be careful. What do we want to define as x? We'll define this whole thing to be x, or just the numerator. So this is where the algebra can get into play.
The product, right, from x1 to x2 to m.
So you want to make that thing the x? So what I would do here is I would assume, without loss of generality, that x1 times x to the 2m equals, what should I assume that product equals? 1. Because then this right-hand side becomes very nice. What should I assume the y's equal? Also 1. And so now we have x1 over 2, if we let x be x1 plus x to the 2m and y be y1 plus y to the 2m, x plus y over 2 to the 2, over 2 to the m plus 1. This is x over 2 to the m plus y over 2 to the m divided by 2. Right? And we know by induction x over 2 to the m is at least 1, and y over 2 to the m is at least 1. So this is going to be greater than or equal to 1 plus 1 over 2, which equals 1. And that's what we needed to show. You don't need to assume that the products are 1. It just makes the algebra a lot nicer. I don't have to worry about what's going on with all the product terms. And then I need to interpret, well, x plus y over 2 to the m plus 1, that's x over 2 to the m. That's the first arithmetic mean. Plus y over 2 to the m, that's the second arithmetic mean. And then just taking the average of that. So you can see why looking at powers of 2 is so nice. It fits in beautifully. So unfortunately, we only have the result now in the special case when we have a perfect power of 2. So now what we want to do is we want to somehow fall back and just get everything for the remaining values. Okay. Everybody ready now for the backwards part? So we can assume at this point, if n is ever a power of 2, we're fine. So assume n is not a power of 2. Choose the smallest m such that 2 to the m is greater than n. I don't think you actually have to take the smallest m, but we're just safe to do that. So let's look at what we have. We have x1, x2, xn. And we need to have 2 to the m elements. So I'm going to put a common number for all of them from some point onward. A. And we're going to have 2 to the m minus n of these. So now we have 2 to the n numbers total. 2 to the m numbers total. I could put in anything I want here. I'm now in a situation where I can use the arithmetic mean, geometric mean, because we know it holds for powers of 2. The question is, what's a good choice of A? So can you give me some candidates? Who are our contenders?
0.
0 is definitely a possibility, but if we put in 0, then the product is 0 and it becomes trivial. 0 is not bad, but 0 does not work. But close to 0, its friend, 1. So we could take all the a's to be 1. Because that's not going to change the product, but it is going to change the mean. What's another good idea for A? Could do 2, but I'll say that that's going to be similar to 1, and now it's going to have the product changing as well. So there's 2 natural candidates, yes?
The geometric mean of the first n things?
Yeah, geometric mean of x1 to xn. And there's one other possible candidate. The arithmetic mean I'm using the letter A because it's the first letter of the alphabet. Which would you choose? 1, the geometric mean, or the arithmetic mean? You've got 3 choices. You can try all of them, but I do claim one of the choices is more natural. You're going to be looking at x1 plus xn plus 2 to the m minus n a's divided by 2 to the m versus x1, x2, xn, and then you'll have a to the 2 to the m minus n to the 1 over 2 to the m minus n. So what do you think is the best choice for A? Yeah.
Is it 1?
So if you do 1, you're then going to get this new factor of 2 to the m minus n. Yes? I would do arithmetic mean because this sum over here is just n times a, right? This sum here is n times the arithmetic mean. So if you choose this to be the arithmetic mean, then this becomes 2 to the m times the arithmetic mean, and this will just become the arithmetic mean. So if you're not sure, if you can at least write down the candidates, you can then have 3 pieces of paper. And in each one you can start working and see, does any one of them have algebra that looks good? And if the algebra is not looking good on one sheet, put it off to the side, try the next one. I can't remember if I told you about the complex exam I took as an undergrad, where after filling up 2 pages, did I tell you the story? Okay, just you personally. Okay. After filling up 2 pages with algebra, I wrote in my exam booklet, there's got to be a better way of doing this, and then 4 lines later, I'm done. And the professor wrote in the margin, it's about time you realize that, Steve. And he was right to put that in my exam booklet. Because it can't be that bad of a calculation. Now, in the real world, you don't necessarily know. But in a problem-solving class, in a math competition, there's an elegance going on. And if the algebra is getting overwhelming, it doesn't mean you're wrong. It just means that you're probably not going down the best possible path. And it might be worth trying another approach. So we will choose A to be the arithmetic mean of x1 through xn. And now what do we get? We now get n times a plus 2 to the m minus n times a over 2 to the m versus x1 xn a to the 2m minus n to the 1 over 2m minus n. So from this point onward, it is just algebra. So I have not bothered to prepare the algebra for today. I will try to do the algebra live. There's a good chance there'll be a small mistake, so please pay attention. Yes?
Sorry.
Already made a mistake. Okay.
A lot of the geometric mean on the right, is it not 1 over 2 to the m?
Oh, you're right. It's just 1 over 2 to the m. Thank you. Yes. So I told you there'd be an algebraic mistake. Great. Now that we've made the algebraic mistake, now the rest of the calculations will be correct. Excellent. So this side just becomes a. Oh, well, wait a minute. I've got a versus here. Do we actually know what that is? I claim we actually know what the versus is.
Greater than
Yeah, greater than u. Why?
we just proved it for powers of 2.
Yeah, we just proved it for powers of 2. Right? We know it's true for powers of 2, so we know this is true. What we want to do now is when the dust settles, we want to be left with the arithmetic mean of x1 to xn versus the geometric mean. Okay? So now we have a greater than or equal to x1 xn to the 1 over 2 to the m. And now we'll have a to the 2 to the m minus n over 2 to the m, so it's going to be 1 minus n over 2 to the m. Yes? Okay. I've got a to the first power on both sides, so that cancels. I'll bring a to the 2m over n to the both sides. So I have a to the n over 2 to the m is greater than or equal to x1 xn to the 1 over 2 to the m. Well, what power should I raise each side to? 2 to the m? Not quite. 2 to the m? Nope. You just require me to do one extra step. I'm going to just use a little bit more chalk. I'll raise both sides to the 2 to the m, and I get a to the n, x1, xn. And now I take 1 over n of both sides. And so now I've got the arithmetic mean of x1 to xn is greater than or equal to the geometric mean of x1 to xn. And that finishes the proof. So this is a really great example of backwards induction. You prove it at a nice sequence of points, and then you have the freedom to choose. This is very similar to the auxiliary lines in geometry. Right? I am deliberately not having you prepare for classes. This is the only time I ever teach a class at Williams where I do not tell students, spend at least an hour reading stuff beforehand. I really want you to be looking at this live and trying to think, how would you attack this? The more times you do problems like this, the easier it gets. Okay? All right, so we have about 10 minutes left. Where we were last time I taught this class, my daughter actually had no school. This was part of a very long period of time when we just had massive amounts of snow cancellation. So we did a game for the rest of the class. So we have a guest here. Would you like to play a game? Free admission to Williams if you beat me.
This is going to be like NIM or some other big game.
So what do you know is true if I'm offering you free admission?
I'm not going to win.
That you're not going to. Right. So the question is just which way do you not want to win? I can give you a game and I'll tell you which side I will take, or I will let you choose if you want to go first or second. I mean, they're all good games, and we're going to get to all of them anyway. It's going to be rigged, so do you have any preference as to how you lose?
No.
Do you want to play the triangle game?
Sure.
Triangle game is a fun game. So the way it works is the following. I draw a large triangle, and then I'll break it up into smaller triangles. And I put a 0, a 1, and a 2 here. On this side, you can only use 0s and 1s. On this side, you can only use 0s and 2s, and on this side, you can only use 1s and 2s. And we're going to take turns, and we're going to put down numbers. My goal is to have at least one internal triangle have all 3 labels. Your goal is to make sure I can't do that. If you can prevent me from doing that, you will get free admission to Williams.
What's the internal triangle? Is it one of 4?
It's one of these. So any triangle. So this would count as a triangle. This would count as a triangle. A big thing like this doesn't count.
Oh.
It's going to be either this triangle or this triangle. Do you want to go first or second?
I'll go second.
All right. I'll even give you a bit more of an advantage. You can go and put the 0s, 1s, and 2s wherever you want. I won't even play. So at this point, I can't be nicer. Or if you want, I'll even you can make the worst possible move you want for me.
I didn't really. That's what I said. I was like, you're so tall.
Well, yeah, and also the internal ones. So, for instance, what would you like to start over here? It's got to be either 0 or 1.
Oh, 1.
Or 1. What do you want to put here?
0.
And here?
0.
All right. What do you want to put here? We've got a 0 and a 1, so.
A 0.
Okay. We've got a 0, a 1. You want a 1 or a 2?
A 1.
A 1. So now, if I could go here, I would just win now. I'm being nice. I hope I do not regret this later. What do you want to put here, a 1 or a 2? Probably a 1.
Yes.
All right. What do you want to put here, a 1, 2, or 0?
A 1.
All right, a 1 or a 2?
2.
You've got a 2 or a 0. I'm going to assume you don't want to put a 0, so I'll assume you'll put a 2 there. You don't want to put a 0 here, so I'll assume you put a 2 here. You've got to put a 0, 1 or a 2 here. You don't want a 0. Do you want a 1 or a 2?
I want 2.
No.
Thank you so much. There goes your pizza. And Darwin's going to take a hit now. All right. So if you put a 2 there, we get a 0, 1, 2 triangle.
I see.
So what do you want to put there now?
A 1.
So you put a 1. All right. So now you don't want to put a 0 here, and you don't want to put a 2 here. So no matter what, you lose. So which way would you like to lose, with a 2 or with a 3?
Take the 2.
You take the 2. I mean, at least lose big. There you go. All right. So, not surprisingly, I won. There's not enough data here. Okay. Let's play another game really fast. I'll leave this as a 2, and let's just change a couple of things. Let's go 2, 2, 1, 0, 0, 1, 2, 1. All right, now I've got a 0, 1, 2 triangle here. Yes? Oh, I can't put a 1 here. I'll put a 2 here. So I've got a 0, 1, 2 triangle here. Anything else?
There's one bottom.
And there's one on the bottom.
Upside down.
Left.
Right here?
No.
Right
Right.
next to there, yeah. Between them.
Between them.
Up, right
All right, there we go. All right. So, unlike the last game, which you played very well, I mean, I just barely kicked your ass in that game. This game, I mean, I got 5. What do you notice about those numbers? They're odd. Do you think it's always odd? Yes. This is a terrific way to prove something exists. You prove the number of ways it happens is odd. And what's the smallest odd number? 1. So I know when we play the game, the number of 0, 1, 2 triangles has to be odd. Therefore, there will be at least 1, therefore I win. Sadly, there's a lot of things in mathematics like that. So rather than studying the triangle game, what game should we have played first? What's an easier game than the triangle game?
Tic-tac-toe.
No. It's gotta be it's gotta be similar to this, right? And actually it would be tick. The line segment game. So if you look at the line segment game, you want to avoid having a 0, 1 segment. As you come in from this side, you have to always be putting in 1s or you lose. As you come in from this side, you always have to put in 0s so you lose. So you can clearly prove that you're going to lose. But I want to prove more. I want to prove that the number of 0, 1 segments is always odd. So you either have your 2 zeros, you have a 0, 1, or you have a 1, 1. By symmetry, a 0, 1 is the same as a 1, 0. Let's look and see what happens when we put in an internal segment. If this is a 0, there's no change. And if it's a 1, we increase by 2. So does everyone agree that no matter what I put in here, I change the parity of 0, 1 segments by 0? Over here, no change. Doesn't matter what I put in. I had 1 before, I'll have 1 after. And now over here, it's the same thing. If I put in a 0, I increase by 2. If I put in a 1, no change. So as I keep putting in these partition points at every moment in time, the number of 0, 1 segments is the same as the previous level, or 2 more than the previous level. And since the initial level has 1, you know that there will always be 1 and will propagate downward. This is the one-dimensional case. Two-dimensional case is a bit more involved, and then from the two-dimensional case you get to the three-dimensional case. This leads to a fixed point theorem. So if you've heard of John Nash and his Nobel Prize in economics, his Nash equilibrium comes from the existence of a fixed point, of a function where there's an input such that f of x equals x. It turns out almost all of mathematics can be turned into finding fixed points. And this triangle game is actually the way you prove the existence of fixed points in some settings. So the idea is to take your really good math theorems and convert them to games, and then beat elementary school kids. So now if you want to play this with kids, because it's good to know how you can explain mathematics. I tell people, look, I'll play you. If we alternate moves, that's going to be much harder for me. If you win, I'll give you $20. If you get 2 moves for every move I do, and you beat me, I'll give you $10. If you get 4 moves for every move I do, I'll only give you $5. But no, okay. The amounts don't really matter. But he goes, let's go for the 20. And then he goes, no, let's play it safe. Let's go for the $1. So you always want to think, showmanship. How do you explain mathematics? A lot of the stuff we're doing, if you ever need to volunteer, if you ever need to give a math lecture, these are things you can do. And you just want to think, how do you want to present? All right, this is a good place to stop.